Okay, this video is for, we're preparing for the third test in calculus, and this is the review for quiz number 10. The main topics here are u-substitution and average value of a function. Okay, so what we see here is that the antiderivative, I could choose to ninth power this thing out, which is not going to happen, or I could recognize that this is a function inside of the other function. Okay, so when that happens, what we do is we set the inside equal to u. Okay, so the inside in this case is 1 minus 2x. Most of the time from this place right here, we can just find the derivative of u, which is du. The derivative of the other side with respect to x is 0 minus 2 dx. The derivative of x is dx. And now we want to match. So right now I know I have the integral of u to the ninth. Okay, so I can just take this, replace it with u because it's equal to it, to the ninth power. Now I can't replace dx because I need to know what dx equals. So the way I do that is I divide both sides by the negative half. And in this case now I have negative 1/2 du. So all my variables have to match, du, and if I had limits of integration still on these, they would also have to be in terms of u. All right, this negative 1/2 can be pulled out front, okay, or I can just leave it there because what I'm going to do now is the antiderivative. So this is just a constant sitting in front. I could have it out front here or in front there. But u raises its power to a 10 and divides by 10. We also have that 1/10 is going to get multiplied by the negative 1/2. Okay, and so when I multiply these together, that's going to give me negative 1/20. The u now switches back to 1 minus 2x because that's what it technically equals to the 10th power, and because we did not have limits of integration, we need a plus c. So there is our antiderivative with respect to c. If you wanted to check it, you could actually just do the derivative and see if it recreated the inside. Okay, for 10, again, locate the inside. Okay, the inside of this, okay, is 1 plus cosine t. So I'm going to go u equals 1 plus cosine t. Therefore, the derivative of u is du, and the derivative of the other side is 0 plus negative sine t times dt. Okay, so right now I can make u replace the inside here, and I could make that u to the 1/2. Okay, but I haven't made the sine t and the dt go away. So I want to match sine t and dt, which is close. I just need this negative sign to go away. So negative du equals sine t dt. So if I replace this with negative du, now I have everything switched over to u's. So the radical is now u to the 1/2, and the dt and the sine are replaced by negative du. Okay, the antiderivative here is u to the 3/2. We divide by that, okay, and that has a negative in front from here. We switch it back from u's back to t's, 1 plus cosine t to the 3/2, and put a plus c at the back because we did not have limits of integration. All right. Now, one other pattern we're going to see for 17 is that as derivatives are performed, they typically drop in power. So a tangent going to a secant and so on. So the inside most thing here is tangent. Okay, so if you consider this like it is tangent theta to the third, the tangent is inside of a third. That is the inside most thing. Now, you're going to see a pattern here as well. So when when u is set equal to tangent of theta, then my derivative looks like secant squared theta d theta. So I can replace secant theta and d theta by du. The tangent is now u, so I am down to u to the third du. So it's a nice cleanup. The tangent to the third is the u to the third. The d theta and the secant squared theta came from what happens when the derivative is performed from this step to this step. So all of this is replaced by du, which is nice and clean because now I have 1/4 u to the 4th, which I switch back to 1/4 tangent to the 4th theta plus c. All right, on the other side over here, the insidemost piece of this is this pi over x. So I'm going to set u equals to pi x to the negative 1. Technically this x was underneath the pi, but this is how I want to see it, so that when I do the derivative du, I'm going to have negative pi x to the negative 2 du. Now, making this look like that piece right there, what I have and don't have, I've got the x squared on bottom, which is where this is going to go, and, excuse me, this is dx, not du. Okay, and I've got the dx. What I don't have is this pi and this negative. So I'm going to actually take that and move it to the other side by dividing it. Okay, so I have du divided by negative pi equals 1 over x squared dx. So when I set this up, because I set u equal to pi over x, I can do cosine of u. All right, so this piece has been replaced with respect to u's. Now
They're called 2500.
The x squared on bottom and the dx, okay, are both replaced by the du over negative pi. Okay, so at this point, this is just a constant I could put in front. I haven't done that yet, so let's do that now before I actually do the antiderivative. So any constant that is multiplied by every piece of this, which this is, can be pulled in front, and that constant would be negative 1 over pi. And it could just sit in front as the derivative is performed. Now, cosine has an antiderivative of sine. I still have this negative 1 over pi. Now I have to switch it back to sine of pi over x plus c. And we are done. All right, the next one. Now we have limits of integration, so we have to do something extra to the problems we just saw. So the first thing I'm going to do is I'm going to figure out the antiderivative. So there's definitely a function inside of a function. This is the outside function, this is the inside function. So once again, u equals pi t over 2. So technically I have pi halves with a t next to it. Okay, so it looks kind of goofy, but the 2's on bottom, and I'm going to put that underneath the pi with the t next to it. So this is going to be the easiest way to perform a derivative. So the du equals pi over 2 dt. Okay, and at this step, what I can now do is I'm trying to match things up. So right now I've got cosine of u, and the dt is going to be replacing something. So I need to get this pi over 2 out of here. So I will multiply by its reciprocal, which means that I'm going to have 2 over pi du equals dt. So here I have 2 pi du replacing dt in my integral. Now I have to stop writing the limits of integration here because I need all of the terms to agree. So this is a u, this is a du, okay? But I can't use 0 and 1 because those are in terms of t. Okay, so what I can do is I can replace the 0 in terms of u, and I can replace the 1 in terms of u. Sometimes this is easier, sometimes this is not. So one way to do it is just to not write limits of integration until we make it back to t. So I'll show you that method before we move on, and then the next method I'll do the opposite. Okay, so here we go. The 2 over pi I'm going to bring out front again. Now I have the integral cosine u du. All right, the antiderivative of cosine is sine. I still have 2 pi out front. Okay, now I'm going to switch it back to pi halves t. Now I can use my limits of integration of 0 to 1. So I couldn't use the 0 and 1 until I brought it back to t. So it couldn't be done with u. Now I can do it. So when I do this, now I have 2 over pi sine pi over 2 times 1 minus 2 pi sine pi over 2 times 0. Okay. Okay, so when I type in all of this right here, I end up at 0.637. And that is the area underneath the curve. Now we could verify that on our calculator, and I find the area 701, and we have the same exact answer again. All right, the next one. Okay, this one has two tricks to it. All right, so this is probably the toughest one we've seen yet in terms of the number of ways we can get this wrong. The inside is definitely u equals x minus 1. All right, so the derivative here is going to be du equals dx. So right now, I can make the inside u, and I could radical it, or I could say u to the half. And I've got that. And I could make the outside dx go ahead and switch to du. What I cannot do is replace this x. So I'm going to take this u equals x minus 1. I'm going to solve for x by adding 1 to the other side. Okay, so now I have x and u related this way. I can take this x and I can replace it with u plus 1. Okay, now at this step, I cannot put the limits of integration of 1 and 2 on here. So I can't do that because this 1 and this 2 and these x's and dx's, all those agree and are all x's. These are u's. So if I want to put a number here and a number here, they have to be a u. So I could do what I did last time, and I could wait till I get back to x's and use 1 and 2. Or I could switch the limits of integration. So the lower, okay, uses u equals x minus 1. The lower used to be 1. So now it would be 0. The upper limit of integration used to be 2. So when I take u equals x minus 1, so now I have 2 minus 1, which is 1. So switching from x's to u's changed the limits of integration from 1 to 2 to 0 to 1. Okay, so before I perform this antiderivative, I'm going to distribute this in and make the algebra a lot cleaner. So got the the integral from 0 to 1. Now I have u to the 3 halves plus u to the half du. Okay, this u multiplied by this u, causing the powers to add. The 1 plus the 1/2 created 3 halves. This u multiplied by this 1, creating exactly u to the half. All right, now to perform an antiderivative, I have to raise the power by 1. So 1/2 plus 1 is 2/2, which is 5 halves, and divide by 2/5. The next one has u to the 1/2, which I raise by 1. So a half plus 1 is 1/2, which is 3 halves. Divide by that new power. And now I can evaluate that 0 to 1. Sometimes it's easier to switch over these right here and stay in u and never bring it back to x in order to figure this out. Sometimes it's easier to bring it back to x and so on. And sometimes it doesn't matter. So this one looked about just as equal, just as easy to do it either way. All right, so when I do this one, I'm going to end up with 2/5 1 to the 5 halves plus 2/3 1 to the 3 halves minus, and now I'm going minusing the whole set of things. So I have 2/5 0 to the 5 halves plus 2/3 0 to the 3 halves. Okay, and all of this bracket is 0. It really didn't do anything. So this is kind of hard to see. That was a 3 halves right there. It's kind of on the bracket, but it's 3 halves. But it didn't do it. Any of this right here is zeroing out. So I just have to figure out this front side right there. So when I do that, I'm going to end up at 1.06 repeating. Let's double check that on the calculator. X square root x minus 1. Graph it. Second, calculate 7. Go back to the original of 1 to 2. We have the exact same answer. This one right here. So find f, given that f double prime equals this, and we know the first derivative at 1 equals 6, and the original at 1 equals -2. So we're going to work backwards. So we know this. We're going to go to f prime of x first by doing the antiderivative. So 12 is going to be divided by 3, and 6 gets an x plus some unknown c. Now, here's my x and my derivative value. So these two values will end up finding the value of c here. So the 6 goes here. That's 4. 1 goes in. 6, 1 plus c. All right, now in this case, this is 4 times 1 to the third, which is 4, plus 6 times 1, which is 6, so that's 10. So when I subtract 10, I end up at -4. So f prime of x is now 4x to the third plus 6x minus 4. Okay, so now I have to go do it again. This time we're going back to f. So using the antiderivative here is going to be 4 divided by 4x to the 4 plus 6 divided by 2x squared minus 4, which gets an x plus c. And now we will use this value right here. -2 equals 1 to the 4th plus 3, 1 squared, 4 times 1 plus c. All right, so I have -2 equals, let's see what all these constants are together. 1 plus 3 is 4. 4 minus 4 is 0. So c comes out to -2. So f of x equals x to the 4th plus 3x squared minus 4x minus 2. All right. Okay, the next one says consider f of x equals x squared plus sine of x on 0 to pi. So we have a set domain. Find the rate of change at x equals pi. The rate of change is the derivative. Okay, so when I do this, I'm going to plug that into 2x plus cosine x. So f prime at pi is equal to 2 times pi plus cosine of pi. Okay, the cosine of pi is -1, so this equals 2 pi minus 1. And you could write that as a decimal, or you could leave it like this. Okay, so that is our rate of change at that location. All right, next says find the average value of f on 0 to pi. Okay, the average value of a function is basically the area divided by the width. Okay, so I need to, how wide is this? From 0 to pi is 1 over pi. So I'm doing 1 over pi is going to, essentially this divides us by the width right there. And I have 0 to pi, and I need to then integrate on the function we are trying to average. So you do the original, so whatever function you're trying to find the average value of goes in here. We do the integral from start to stop, and here we usually make a fraction. We put 1 over the width, and essentially this divides us by the width. The width in this case is pi, because it goes from 0 to pi. That's how wide it is. All right, so the antiderivative in this case is x to the third with a 1/3 in front. Okay, sine has an antiderivative of negative cosine, and I need to evaluate that 0 to pi. Okay, keep in mind I also have this random thing out here still. Okay, so let's figure out what this is. So I have 1 over pi. Now I have 1/3 pi cubed minus cosine pi. That entire amount here is going to subtract 1/3 0 cubed minus cosine 0. All right, so I've got 1 over pi, which is still my divide by the width. So this is going to be pi cubed over 3. Cosine of pi is -1. That ends up being a +1. All right. In this case right here, we end up subtracting 0. In this case here, we're adding cosine of 0, which is 1. So again, we're subtracting what all this comes out to, and all of this comes out to 1. And we then clean this up. So this is going to be a 2, and I'm going to bring the pi in. All right, so there's a lot of different ways you could write this. One way would be like this. Pi over third has 3 pi plus 2 over pi, which still cleans up further to pi squared over 3 plus 2 over pi. And that's kind of ugly. Okay, from here, so I can calculate my area, my integral, 0, enter, and we're going to pi. Okay, so I have 12.335. If I take 12.335 and divide by its width, 3.926. Got it. Exact same answer. All right, find the value of this given that the integral 3 to 0 of f of x equals 4 and the integral 3 to 6 of 2 times f of x dx equals 20. All right, so I need to construct the different areas here. So it appears that we've broken it into 0 to 3 and 3 to 0. Okay, so I need to know that the integral from 0 to 6 is going to be equal to the area from 0 to 3 plus the integral from 3 to 6. Okay, so this piece right here is in the wrong order. If I choose to reverse the limits of integration to 0 to 3, I have to put a negative out front. Okay, so what that does, f of x dx equals 4. And because I want exactly the integral from 0 to 3, I'm going to move that negative to the other side by dividing or multiplying by -1. So this piece right here is -4. All right, let's get this one to match exactly the integral from 3 to 6. Okay, so I need to get that 2 out of there. So I bring that out front, 2 integral 3 to 6 f of x dx equals 20. And to make it match exactly, I divide by 2. So when I divide by 2, I get 10. So the integral piece from 3 to 6 is 10. So this whole thing comes out to 6.